Morning, everyone. So we're going to continue our study with energy. So far, we've looked at two types of energy. One is moving energy, so EK. This is kinetic energy. We had a formula of 1/2 mv squared. For moving energy, especially when I slow down, the energy has to go somewhere. It gets stored somewhere. In yesterday's lesson here, we had introduced EP, which is potential energy. There's many different ways energy can be stored. The formula I gave you is specific to gravitational potential energy. It's stored energy because I'm off the ground. So far you'll get mgh on your formula sheet as well. Let's just recap here. Energy is a conserved quantity, just like momentum is conserved. I already drew this diagram for you, I think, last week. Let's imagine my entire universe here fits inside this box, definitely not to scale there. When we say, this is actually the first law of thermodynamics, energy conservation. So first law of thermo. And basically it says, it's another restatement of conservation of energy. There are only a few things in our universe that are always completely conserved. So conservation of energy here, anytime you have a conservation law, you would say things like, energy cannot be created or destroyed. Whatever energy our universe had millions and millions of years ago is the same energy that we have here. Sure, the quality has sort of degraded. The quality is sort of spread out. That's probably something that's bad for our universe here. Even though the total number hasn't changed, the amount of energy that's still useful to provide useful work has decreased, but at least the total number hasn't changed. In this case here, energy cannot be created or destroyed, but just like momentum here, it can be transferred between objects, but it can be transferred. So it can be passed from object to object, and energy also has one added feature. It can also be transformed. And what we mean by transformed is it's still energy. It's still going to be measured in joules. It's still going to be a scalar, but it actually can convert forms. So say that example that I just did here, if I have two particles zipping towards each other, because these particles here have electrons on the outside, and I know similar charges want to repel each other, that force of repulsion here will actually cause these objects here first to slow down. I was trying to speed towards each other here. As I drop kinetic energy, I have to have stored that energy somewhere else. The energy had to have gone somewhere. So I can trade kinetic form for potential form, or after these things here collide, when they're trying to leave each other here, they're very happy to sort of zip away from each other. So therefore, it would start speeding up. Well, where did it gain that kinetic energy from? Energy can't poof out of nowhere. We actually had to have traded it back from potential energy. When we deal with conservation of energy as a law in our universe, we're applying that to the entire universe all at once. So like I mentioned, the total energy, the total number of joules, if you believe the Big Bang, all the energy in the Big Bang, whatever energy number that started with, even though our universe since then has been accelerating and expanding away, that total number here hasn't changed. So the quantity of energy hasn't changed. Obviously, you know the universe is a huge place, so what we do instead in physics and in all sciences, we actually just choose a really small fraction of the universe. Okay, again, not to scale. The small portion we're going to look at is going to be referred to as a system. This is the part that's under study right now. That's the part, maybe the collision. Today we'll switch over to roller coaster style problems. That's the part that you're interested in. Everything else around it, we're going to call it the surroundings. So it turns out conservation of energy, that law, is a little bit less restrictive than the conservation of momentum one. Conservation of energy applies to the entire box, but if my system, let's say there's a car crash, let's say there's a huge sound to it, my system may actually lose energy as sound energy. Maybe the wheels will sort of scrape along the ground and actually lose heat energy. It's possible that what I define as my system may actually lose energy if I consider what sound energy comes off from the car and what goes in the surroundings. Yes, the total is the same, but at least I can have a local transfer. So hopefully I can show you that picture here. I can have a local transfer. It could be a local loss of energy. So my energy could be a negative energy. Well, in this case, I thought energy is supposed to be scalar. In this case here, negative just means lost to surroundings. Or I can have energy input to the system. Let's say I'm doing some cooking and I'm using a gasoline burner and I'm putting fuel and I'm actually adding energy to it. I can have a positive energy. We're not using positive and negative in this chapter to indicate direction anymore. We're using positive and negative to indicate, based on what I define to my system, this positive energy means my system actually gains energy. Right? the energy of what I had defined at this moment actually goes up or goes down depending on which part that I'm looking at it. Just for completeness sake here, when we did this similar diagram here on the momentum lesson, momentum was also conserved. It had to be the same before and after. Momentum conservation was true for the whole box, just like energy is, but momentum conservation was a little more restrictive. It even had to be true for the system. So I didn't care whether we were dealing with a bomb problem or a collision problem, even for just that 2-particle, 3-particle collision, inelastic or elastic here, all the momentum, make sure the tendency of motion is all accounted for. We saw that only in the elastic case did kinetic energy also get conserved. So that's why I say conservation energy, it's sort of like momentum. It's conserved. It's a same number quantity, but it's not as restrictive because it only applies to the universe. I can have a more local transfer, local transform of energy as well. So far, when we've been doing questions here, we've been looking at sort of the kinematic and the forces equivalent. I could have answered it based on our impulse stuff and based on the earlier chapters. We're going to start looking at problems today which only can be answered using energy. So let me give you just an example of this here. Let's imagine I start off with we're going to eventually get to a roller coaster style problem. So let's imagine I have a roller coaster that's really on the top. Right? It's going to be sort of zipping away. Right now it's just sitting there. We're going to imply that it's at rest. It's some distance h off the ground, and then it's going to eventually follow the track and eventually hit down here. If you've been on any roller coaster, you know you're going to be traveling quite fast down here, right? So that's a typical setup. Let's first try using our kinematics and our force sort of understanding here. Why doesn't it work? The problem is, especially for a roller coaster style problem, you'll notice that this trajectory here is actually a curve. Meaning, although you may be able to do like a force analysis here, you might be able to do the force analysis at this particular instant. An instant later, it may not have shifted by a lot, but an instant later, my direction is now changed. Now I need to redo my calculations. An instant later, again, my direction has changed. My acceleration, my friction, and my how much is down part of gravity, all that has changed, and it will constantly change. It's only staying that way for a very split second. It's impossible for doing all those little mini analysis here until we get to the final thing. Let's just switch over to our energy concept, and it turns out energy is actually a whole lot easier. Because of energy conservation, what we can say, yes, I know this is my system, but what I can say is initially, I know this thing here was at rest, and I know this one here was initially above the ground. So it did have some initial energy. I'm going to call the final position the instant where it hits the ground here. And I can use this sort of energy conservation law. I can totally avoid this problem of having direction and vectors and angles and whatnot. I can avoid it because energy itself is just a pure scalar. So let's look at the energy conservation laws again. We're actually going to eventually develop what's called a work energy theorem. Sounds very fancy, but I'll show you where it comes from here. Work energy theorem actually comes from the work definition. So far, we've had two formulas for work. Work can be force times distance. I just mentioned force would be a nightmare to try to solve this because force needs direction and the direction keeps changing. I won't be able to use that formula this time. But for the work energy theorem, we also were able to derive work is actually a change in energy. If it weren't for the work that I do, the energy wouldn't change. So based on that here, we already had this definition. The work is equal to E final minus E initial. And in fact, all I'm going to do is I'm going to add the E initial over to the left-hand side. E initial plus work is equal to E final. You see that it's exactly the same formula, but I'm going to give it a new name because I did some algebra to it. This one here is a really nice way of looking at it. Basically, I have my initial energy. I don't know whatever forms I have. I don't care what roller coaster problem. We'll do a pendulum style problem later on as well. So I have initial energy. I know I'm going to have my final energy as well. Basically, we're saying because work is a thing that causes energy to change, if there was no work, if this W here is 0, I automatically have EI equals to EF. So which is why we call this one here, in general, we call it a non-conservative work. This is something that you do to the system. It could be friction. It could be the people on the roller coaster screaming away. I can't conserve for that because that energy will completely leave the system. But were it not for this non-conservative work, I'll give you examples of that here. Friction or maybe screaming from the people on the roller coaster. I can't conserve for that. But were it not for this work, I can set W equals 0 in most cases, and I can say conservation energy. Even for my system, whatever energy I had at the top of the hill has to match up to what's at the bottom. So that's what conservation of energy looks like. I'm going to always assume that this non-conservative work is 0 unless I'm told otherwise, and I'm going to just try to analyze the system. The one last step to this roller coaster problem here is, sure, the E initial here, whatever energy I have at the top, should match what's at the bottom because I wasn't told I lost any work due to friction or screaming of the people on the roller coaster or whatnot. But what I do have to ask is what forms of energy that I have. So far for the two types of mechanical energy that we have, mechanical, again, it's sort of energy dealing with moving parts. Mechanic energy, sometimes they call it total mechanic energy. We're only looking at forms like kinetic, like moving energy, and like potential energy, stored energy for being off the ground. So in this case here, you just want to analyze, am I moving? Well, no, I'm at rest. So in this case here, I have no EK. Because I'm at rest, however, I'm held this height off the ground, I definitely have an EP. This time, although for my E initial, although I could have had for example, an EK initial and an EP initial, that will be different in the questions that we do afterwards. At first, in this problem, we're at rest, so this one here is 0, whereas this one here would be defined as an MGH. Fine. So whatever my MGH is, I had assumed that there was no losses, so W is going to be 0 in this problem. That also has to equal to all the forms of energy I have at the end. Again, the mechanical energies I've done so far is just kinetic and potential. Ask yourself, do you have kinetic and potential at this last step? Hopefully you were able to say, well, because I am going to be moving, I'm going to definitely have some kinetic energy. It's going to be in this heading, but again, energy part of it just gives me the speed of it. It's a scalar. But because I'm back down on the ground, you notice, again, now I have no potential energy. It doesn't always need to happen this way, but in this case here, I started off here. I was top of the cliff, okay, top of the roller coaster. I had all the energy stored away. At the end, I could have had some kinetic, I could have had some potential, but in this case here, because I'm completely on ground level, this one here again is 0. And basically what's happened here is I've taken all the energy that I've locked away by dragging you up the roller coaster. That's why the first part of the roller coaster is always really boring. It takes a lot of energy just to rock your way up to the top. And then once you're at the top, we just let gravity do the rest of it. We just let these energy conservations change throughout. And essentially what's going to happen here is we're going to have the kinetic energy. This is me moving at the bottom. And in fact, I would imagine if all my energy has now been converted to moving energy, I'm going to be moving the fastest at the bottom. So let's just try out this formula here. I know I haven't given you numbers. It's a little bit kind of crazy. I can actually ask you this question. So I have mg. Let me just specify this is going to be h initial. This is when I'm at the top of the cliff. Right here, that energy that I have is supposed to equal, because I assume that there was no losses due to friction or whatnot, has to equal the kinetic energy, the half mv. Careful, the final energy is talking about this position. So yes, in some sense, we're talking energy conservation. I'm not saying potential at the top equals kinetic at the top. I'm saying potential energy at the top, because the potential at the top slowly gets traded away for kinetic energy. By the time we're at the bottom, all that joules, I use money as an analogy here. Imagine all my money is in a potential energy account. By the time I get to the bottom, I want you to transfer your money from the potential account to your kinetic. So therefore, I have none in my potential account. But if all that money and all that joules is now converted into kinetic, how fast would I be going? So yes, energy conservation, but I do want you to emphasize here, this is talking top, so it's initial and final. We're not saying the starting values are equal or the ending values are equal. I'm saying the top stored energy is equal to the bottom kinetic energy. If you look at this formula here, you'll notice there's an m on both sides. I can actually divide m on both sides. That means, physically speaking, your velocity at the bottom doesn't care what your mass is. That seems a little bit surprising because I would have thought, well, if I'm a heavier object, I'm going to have a lot more kinetic energy. I'm going to be much harder to stop. But it turns out, sure, if I lift up a heavy object at a distance of h, I needed to put in more energy. But it's also harder to move that heavy object around. Lighter objects are much easier to accelerate. I may have put in a lot more energy to lift the heavy object upwards, but because the heavy object is also really hard to move, the mass term actually cancels out. So whether I was a 1 gram coaster and a 1 gram coaster, or a 100 gram coaster and a 100 gram coaster, the velocity at the bottom doesn't matter. What does the velocity matter on, though? Based on our formula, it's going to depend on what our gravitational field strength is. It's going to depend on what we're going to put as 9.8 because we're on the Earth's surface. it is going to depend on the height of the roller coaster. The farther up you lift me, you would have had to exert more force. It would have taken longer to get you to store that much energy. That's actually going to translate into more kinetic energy, more velocity at the end. So I can actually rearrange this expression here for v. I'm going to bring the 2 up first. So 2gh is equal to vf squared. It turns out your vf, your speed at the bottom, is just given by the root 2gh. So what was an impossible problem with kinematics? Kinematics was, I need to deal with every single angle and break down components and whatnot. I dealt fairly simply just with the energy conservation law. Well, all of it was stored at the beginning, and all of it is moving energy at the end. In fact, I only analyzed this roller coaster at 2 specific instances. I could have actually asked you this problem. We'll see this in the next question. I could have asked you anywhere midway. And really, the way to understand this here, think about, we have E total. So the total energy that I have, we have a potential energy account, and we have a kinetic energy account. At the beginning, I have all of it stored away in the potential. I have nothing in kinetic. By the time I get to the ending, I have transferred all my money. It's the same money that I have. I don't suddenly get more money or less money. But what I've done is I've transferred all the potential over to kinetic, such that I have no more stored energy. I'm back on ground level, and now I have all of that as kinetic. So basically, I've traded, it's the same total joules of energy, but I've traded all the energy used to actually move me. This is actually applied for all sorts of different positions. So let's say I was sort of 2/3 of the way down. I could also ask you the question here, well, how fast am I going at that instant? Intuitively, you'd say it's probably not going to be as fast as the speed that I just calculated, because in this case here, ask yourself what type of energy that you have. In this case here, I still have an EP of being this height off the ground. Again, the h here is a little bit tinier, so the amount of stored energy I have is a little bit less. That's sort of like in my process of trading my money from potential to kinetic, I'm in the midst of trading, I still have some in my potential energy account, because I'm still some height off the ground. I still have some in potential, but what's not in potential anymore has now been traded over kinetic. That kinetic hasn't quite reached its peak yet, and kinetic is the moving energy, so therefore my velocity here is not quite as big as the really bottom as well. Again, we're going to see this a little bit more in the next question, but there's this constant interplay between these are the 2 different types of mechanical energies, motion style energies, and all we're doing is we're moving it from place to place. We can always assume that the non-conservative work is 0. We're going to see a question, what if it's not 0? It's a fairly easy problem to deal with anyways. Right? So without further ado here, let's actually go to a straight roller coaster style problem. These problems here should feel fairly simple because we're not having to deal with forces and vectors and free body diagrams and whatnot. We just deal with energies as scalars. So let me do the same startup here, but I'm going to give you some numbers. There's my roller coaster. I'm going to start off, my roller coaster here is a 600 kilogram roller coaster. The first height here, let's make it a 100-meter high cliff. So this roller coaster first goes down and then comes up a little bit here. Let's say that's a 40-meter high cliff. I'm going to tell you that this roller coaster, just like all roller coasters, they drag you up to the top and they basically just leave you there just enough momentum to actually push you over the hill, and actually it's just gravity that takes you the rest of the way. So based on that, I'm going to ask you a similar question here. Can you find the velocity for me at this point? Let's call that part A. And can you find the velocity for me if I'm on part B? It's an exact analysis of what we did earlier, but it's just with some numbers. So we start off with our work energy theorem. E initial, if it weren't for work, it's supposed to be E final. Because nobody told me about any energy losses, I'm going to assume that the work is 0. So I'm going to assume to apply conservation of energy, not just to the universe, which is always true, but also the energy just to this roller coaster problem. So no one's screaming, there's no heat loss to the environment, there's no loss to sound energy, there's no non-conservative work. What you want to ask yourself here, you want to start off and try to figure out what is your total bank account. I don't care if it's in the potential account or the kinetic account, I just want to know how much money that you have. In this case here, because I'm given the most information at the beginning, I'm going to start off by saying my total bank account is supposed to be, could be KE, could be PE. Or you can say E subscript K, E subscript P. You're going to ask yourself, all right, so I want to know my total number, how many joules that I have. In this case here, just like the problem before, we are at rest. Being at rest means I don't have any kinetic energy. So in this question, right at the beginning at least, all my energy is still stored up. My stored up account here is MGH. So let's try it there. to find the E total, that's at the top of the hill. All of it in this problem happens to be potential. I'll say PE initial. This is going to be mgh. I'm a mass of 600. Gravity is 9.8. I don't need to worry about positive or negatives because energy is going to come out as a scalar, positive anyways. And my height happens to be 100. This is just going to give me some random number here. 600 times 100 times 9.8 gives me 588000. Even from yesterday, we started seeing these numbers get to be fairly big, which is why usually in this context, we typically go to kilojoules. This would be 588 kilojoules. 1,000 joules is a kilojoule. So would you agree this is the total amount of money that I have? I don't care if the roller coaster later on is just sort of midway down, all the way down, or whatever. Even at these two special points that I look at, this is the total money that I have. It's conserved because there was no work that was done. It's just because I have the two accounts, I can be trading it from potential to kinetic. So that's what we're going to do in part A. So part A, ask yourself again, well, what are the forms of energy that I have? The two forms I dealt with could be an EK or an EP. Just getting you familiar with a lot of different ways of writing it. In this case here, I'm actually back on ground level. So in this case, H is equal to 0. At A, I actually have no potential. That's like trading all my 588000, but trading it all to become kinetic. So in this case here in part A, all energy, just going to write in words for you here, all energy is kinetic. So in this case here, I'm going to say EK is supposed to be 1/2 mv squared. If I've traded my 588000, I transferred it to my kinetic energy account. If I have all of my money in the kinetic account, all of that's used to move a 600 kilogram mass, what is my velocity? So it should be fairly easy. Take that 588000 times 2 divided by 600 with the square root. This one here gives me my final velocity. Again, what would have been an impossible problem using kinematics, there's too many changes in direction, super easy calculation with energy, right? Because of energy conservation, I know because you were this high off the ground, because we're on the Earth's surface, you will automatically be 44 meters per second. That's almost 100 kilometers per hour on the bottom. So that's for part A, no problem. Part B is a little bit more interesting. Part B would have actually applied to even this spot on the roller coaster, but just for simplicity here, I just sort of put on another bump here. Again, what you want to ask yourself here is, what are the forms of energy that I have at part B? The forms of energy that I have, the total energy, is split up between kinetic and potential. This time it's not so simple. This time it's not like 0 in kinetic or 0 in potential. This time I actually do have both. I would expect the roller coaster would still be moving, so I still expect to have some money in the kinetic account. But because I've come up off the ground, I would expect some money now back in the potential energy account. So basically I had transferred potential all to kinetic, and now I switch some of the kinetic energy, I trade some of that back, I store some of it back as potential. The potential here is less than the potential at the beginning, however. The potential at the beginning was being 100 meters off the ground, whereas the potential here is only being 40 meters off the ground. So when I try to do an mgh here, I'm actually going to see that's actually a little bit tinier. So I'm going to try out that there. My E total, my 588000, that was the total joules I have throughout this roller coaster. This time is divvied up between kinetic and potential. Sometimes you have enough information to find the kinetic part and will be asked potential. In this case here, it's vice versa. I know most information. I actually know the height. I don't know the speed again. So in this case here, I'm going to take, well, I had 588000. My formulas are going to be 1/2 mv squared, and I have an mgh. This time I can just punch in the numbers as I have them. So my E total, 1/2, I'm 600 kilograms. I don't know my speed, so I don't know that V there. But I do know now I have 600 times 9.8, but this time only being 40 meters off the ground. Just for comparison's sake here, I'm just going to type in that last part. 600 times 9.8 times 40. This one here gives me 235200. Using that sort of money analogy, my total money is 588000. I still have two energy accounts. I still have the kinetic account and I still have the potential account. Now I know how much is in the potential account. I should be able to figure out by difference. 588000, I minus off the 235200. Oh, in the kinetic account, I still have 352800. So I want to emphasize by doing this question here, the total energy has not changed. I was able to find the total energy at the top. This 588000 is the total money that you have. But you still have two bank accounts available. You can constantly be transferring funds back and forth no matter how you like it. In this case here, because I had information, I knew how much was in potential. Looking at the numbers, you notice this number is a lot tinier than being 100 meters off the ground. That leaves you with the extra money to just move you. So in this case here, I'm going to just write down 352,800 equals 1/2 600 v squared. I'm going to multiply that by 2 divided by 600 with the square root. Gives me a velocity, and intuitively I had expected it should have been slower, and there we go, 34 meters per second. Again, what would have been an impossible question in kinematics, fairly easy using energy. We actually sort of used the work definition, change in energy. We avoided the force times distance because that would be really hard, but this one here is just conservation energy. It's just trading energy from one account to the other. So there's one more problem I want to do with you here. Similar to a roller coaster style problem, on your energy package, you're going to see more examples of this roller coaster. This time I'm going to design my roller coaster a little bit differently. I'm going to have, I'm going to start out a little bit lower, and this time my roller coaster is actually going to do this. Okay. At first, if you were an engineer, you'd say, well, you're crazy. If I only was this high at the beginning, there's actually no way I'm going to get up there. But I'm going to design my roller coaster to actually launch you out from the start. So it actually boosts you out from the beginning here. Let's stick with the 600 kilogram mass because we have a little bit of familiarity. Let's give you a speed. So there's some launcher mechanism on this side here. Let's give you a speed of 25 meters per second at the beginning. So basically you're sitting in the roller coaster. When it says ready, set, go, you get pushed out of this roller coaster. I'm going to give you the height here. Let's say this height. So the height of the starting cliff is 50 meters. And basically, if I'm the roller coaster designer, I want to know how high can I design this second peak here so that I just manage to get over. Okay, so I'm going to treat v equals 0 here. I know I'm going to speed up on the way down. I know I'm going to speed up. I know I'm going to slow down on the way up. So slow down, slow down, slow down. I'm even going to be able to get past my starting height because I initially, again, you can say to yourself, E total is supposed to be kinetic energy and potential energy here. First thing you want to do is you want to find your total amount of money, your total joules. This time, we do have potential for being 50 meters up, but we also have some added bit for being 25 meters per second right out from the gates. In this case here, by the time I reach the really, really peak, I actually have stored all of it. If I trade the remaining kinetic that I had from the launcher, I push that into potential, I'm going to just manage to eke over this peak here. It's all going to be potential here. All right. I'm even going to throw on a like a non-conservative work here. The work or energy loss to friction is, make up some numbers here, is 3,000 joules. Okay, they just give you some static number. Okay. So as the wheels were sort of locking away and sort of rocking down this roller coaster here, we end up losing that 3,000. Okay, so there's our setup. Those of you that are really astute will be able to see this is actually just a reverse of the question we just did. We actually started on the top of the hill. All of it was potential. We had gone down to the bottom. We're traveling the fastest here. We actually were coming up a little bit. I'm not saving all of it in potential, so it's still moving energy, but let's do it in reverse this time. So starting off, it doesn't always have to be the beginning where you're given enough information. I might actually have information for somewhere midway, but essentially what you want to do is you want to find the total energy somewhere. Figure out how much total money or total joules that you have. In this case here, it's between kinetic and potential. The kinetic part is half mv squared, potential part is mgh. You have the formulas for that. So we're going to add these up here. 1/2 600. My velocity is 25 squared. Because of the launcher, I'm not actually seeing the force anymore. I'm not constantly accelerating, but once the launcher has let go, I already had a speed of 25. I already had some money in my moving account. My potential is 600 times 9.8 times the height that I'm on. I know the height is not actually the tallest height. In this case here, it's actually 50 meters. I'm just going to show you these sort of middle steps here. 300 times 25 squared gives you 187,500. 600 times 9.8 times 50, 294,000. Okay, so far what I'm saying is how much total money do you have? Well, I have this much money in the kinetic account. I have this much money in the potential account. Let's just add these two up, 187,500, and therefore my total amount of money is going to be 481,500 joules, were it not for any non-conservative work, we'll deal with this one here in a second here, but were it not for any non-conservative work, this is the total amount of money that you have no matter where you are on the roller coaster. You may be transferring, trading bank accounts, trading energy from one place to the other, but that total energy is unchanged. So now it's a fairly easy problem to do at the really top then. So if this amount of money has to be conserved, we're going to have to lose 3,000 by the end of it. And at the end of it, because we just eke over the second peak, all of its potential, I'm not moving anymore. I just have enough to get over the peak and then fall over the other side, but I have no more kinetic. That's like trading. What would have been kinetic energy at first going down, I would have traded first potential to kinetic. I'm speeding up, speeding up, speeding up. I'm getting faster because I'm not that far off the ground. But especially on my way upwards, I'm going to slow down. I'm going to trade my kinetic back into potential to the extreme that all the kinetic is traded over to potential. In fact, kinetic is not going to be 0, and I'm going to have all my money in potential as well. So on that peak here, so at, let's call it the first peak, what we're going to have is E total is all in the potential account. So if my E total, that's going to be equal to MGH. So my E total, I transferred all my 481,500. That one was E initial though. So far I've been saying it's equal to the ending. Here's where your work energy theorem comes in. Energy initial, were it not for the work that was done, maybe I'll do this over here. E initial, were it not for the work that was done, my E final should be the same. In this case here, I know all of it is potential, but this time I actually do lose money to the surroundings. So 481,500, they give you a static loss of 3,000. So what I'm going to do is I'm going to minus off 3,000, or you can assume it's adding a 3,000. Doesn't really take away much. It's like someone stealing your money as you go to the top of the cliff. And actually, by the time you get to the top of the cliff, we may actually only be 478,500. So although I had said earlier, I know my total money is now all stored in the potential account, our total money is actually going to be a little bit less than what it was before. 478,500, imagine storing that. We're 600 kilogram, we're 9.8. How high up off the ground can we get? If you're the engineer of this roller coaster, how high up can you make this one here? And I'm getting here, you can make it 81 meters. And just like we had seen, it's possible that we are actually higher than what we were before. We were only 50 meters on the starting point here. I'm actually managing to get higher if I trade in some of that motion energy, trade it into the potential. Even with the loss of work, even with the loss of energy to the environment, I still am able to get up 81 meters. Right? So I'll leave the lesson off there. If you have any questions, let me know. Thanks, guys.